Hi everyone, this is Dr. J, and in this lesson I'm going to talk about GPS and strain, or in other words, how GPS or GNSS relates to tectonics. Now you'll see here a couple figures, which are from a paper that I wrote with my master's degree advisor for my master's degree. And in this figure I'm showing you two plots, both from California. On the right, you'll see, on the left, you'll see GPS data. Now, let me just explain what you're seeing in the figure. So you see the outline of California. The red color is arrows, and those red arrows represent individual GPS stations that are obviously covering most of California. The length of those arrows tells you how fast that GPS station is moving, and of course the direction tells you the direction it's moving. You can see the San Andreas Fault in black. That's the thick black line that I've marked on there for you. The other thinner gray lines are other faults and fault systems in Southern California. You see a couple of profiles and some more, a box, which I'll show you what those mean in a little bit. And then very important note here is the scale. So 50 millimeters per year, the length of that arrow is a 50 millimeter per year GPS velocity vector. And these are GPS velocities relative to stable North America. So if you fix North America, have it sitting still, this is how fast these velocities are moving. Now on the right hand side, you'll see a plot which is actually from INSAR. We haven't talked about INSAR yet, but we're going to be getting to that. I'm not going to say anything else about this plot in this video, but we'll talk more about this later on when we get to the INSAR module. So let's look at the GPS data, and I'm going to zoom in here a little bit for you if I can. So you again see those red arrows, and those are telling you how fast that point on the Earth's crust, on the Earth's surface, how fast that point is moving relative to stable North America, essentially where we are here in Missouri. How fast are these parts of California moving with respect to Missouri? And you can see on either side, especially in the central area, on either side of the San Andreas Fault, those arrows are very different lengths. So over here, we're more than 50 millimeters per year. Over here on the right, we're less than 50 millimeters per year. So there's this big jump across the San Andreas Fault. Now the way that we relate this information to tectonics and earthquake potential and earthquake hazards is through the concept of strain. Now strain is related to displacements or velocities through the derivative. Now if you're not familiar with derivatives and integrals from calculus, let's say that we have position x and we'll call it velocity v. And if we make a plot of velocity versus position, could be any particular shape, where let's say this is 0 and this is some number, call it 10. And this is now a plot of position 1, 2, 3, 4, and so on and so forth. So velocity in, let's say, millimeters per year versus position in, let's say, kilometers. Okay? Velocity versus position in millimeters per year, kilometers in terms of the units. So this would just be some profile, not necessarily related to the GPS plot that you see there. But let's take the derivative. So for those of you who've had calculus, I'm assuming most of you probably have, you of course remember that if we draw a tangent line, we take a line that's tangent, so in other words parallel to this line, but it's straight line. So let's take this point here, then the tangent line is going to look something like that, where this is now a straight line. I don't know if I've got that quite right, but it's pretty close. The tangent line is a straight line to this point, or I should say the red line is a straight line which has the same slope as the black line at the point here. So the black line and the red line have the same slope at that particular point. Now the derivative of the black line, if we say now, call that delta x, call this delta y. So if we take the slope of that red line, that's the derivative of the black line at the point given by the red dot. And actually, I'm going to change the location of my dot to make it a little bit better of a tangent line. So right about at that red dot, the slope of the red line and the slope of the black line are equal, and the slope of that line at that point is the derivative. It's just the slope of the line. And of course, we can take the slope of the black line at every point along the line, and that slope is going to change. For example, if we take the point here, and I'll try to do a better job drawing, the slope of the black line at this point is going up. It's a positive slope. Here, the slope is at our original point. Call this point 1, point 2. At point 1, the slope is negative. The line is going down. At point 2, the slope is positive. The line is going up. So this should all be very familiar to you if you've had calculus. If you haven't, this is just called the derivative. It's the slope of the line at each point. And we can actually plot that as a separate curve, where now I'll do it a little bit differently to make it easier on myself. Let's see. So let's go like this, and then let's go like this, and let's go like that. So now the black line is some profile, say velocity versus distance. And if we draw a new x-axis here now, so this is just another, a y-axis, not an x-axis. And let's make this 0 on that y-axis. And we want to plot the derivative of the black line. So if we plot the derivative of the black line, so here the black line is going down at some more or less constant value. So the derivative will be negative. Let's say it's -2 or something like this. And because this line is essentially straight, that's supposed to be a straight line segment right there. I didn't do a great job. But essentially a straight line. The slope of that line is constant until you get to here. And it's at -2. Now once you get to this part, the slope of the line is horizontal. It has no slope actually, so the slope is 0. So at this point, the derivative is right there, and the derivative is 0 because the line is horizontal, the line has no slope. Now notice the black line is not 0, the black line is whatever value it is over here, 4 or so, but the derivative of the black line is 0. Once you get to here, the derivative makes a jump again, and let's just say it's +2, because now the line is going up. So starting at this point, it's again constant because we have a straight, well, supposed to be a straight line segment, and it's a positive value of +2. So this just means that if you take the rise over the run, you would have 2 here and 1 there. So the slope of the line here is +2, the slope of the line here is 0, and the slope of the line here is -2. Hopefully that makes sense. So we take the derivative, that's just the slope of the line at every point. Now if this black line were curved a whole bunch, then the derivative line would also be curved. And that's where strain and GPS kind of connect. So in the Earth, when we have faults, we can measure GPS velocities across those faults. And what we find is that if you have a fault, let's say at x equals 3, let's say there's a fault at x equals 3, and it's running in and out of the board. what we often find is that the velocities associated with a fault like this look something like this. Again, this is 10 to 0. Where you have high velocity on one side. So if this was the San Andreas strike-slip fault, for example, the two sides of the fault would be moving in different directions. This is a strike-slip fault, so the two plates are moving side to side. On the, let's say, Pacific side of the plate, we have high velocity. And actually, in the case of the San Andreas fault, the Pacific plate velocity relative to North America is around, let's just say, 55 millimeters per year. Okay, so that's the high value. And then, again, relative to North America, we have 0. Well, 0 is already over here, I guess. So I will erase that. So 55 down to 0, crossing the fault. And you can see that this curve is kind of anti-symmetric, high and to low, and it's centered right on the location of the fault. So this is a very classic signal that we see from, for example, strike-slip faults. Okay? Now, if we want to look at strain, strain is the derivative of velocity. What's the strain signal going to look like from this curve, do you think? Well, strain is the slope. Up here you see that the curve is almost flat. So the strain, let's say this is 0, will be pretty close to 0. Up until there. Okay? So the strain is around 0 because the slope of the black line is around 0. It's close to 0. It's not quite flat. You can see there's a little bit of curvature, but it's close to 0. Now here, the line actually starts to decrease. So the slope becomes negative. And so actually, we'll start out close to 0, and then we're going to start dropping. And the value that it drops to will depend on, what the absolute values of these velocities are and what the distance is. That will change the absolute magnitude of the strain. Let's say it drops down to some number. We'll just call it epsilon. So it's actually a very small number because the change in velocity divided by these distances, with distances in kilometers and velocity in millimeters, it's a pretty small number. So we typically see numbers like 10 to the minus 6 strain. Something like 10 to the minus 6. It would be a typical value for strain. Okay, so you can see that I've sort of drawn a minimum in the strain curve right at the fault. And again, that's typically what we see. The strain is either minimum or maximum, depending on which sign this line goes, right at the fault. Now, over here on the right-hand side, you see that the strain is, the velocities have gone back to close to flat. So that means the strain, the magnitude of the strain, is going to be kind of headed back this way, and it's going to end up, well, it's not quite flat. It's going to end up something like that, where that is supposed to be a 0. Sorry, my drawing isn't very good. All right. Something like this. So now you can see two things. One is that the velocities change from low to high as you cross the fault, or high to low, depending on which direction you go. And you also see that the strain goes from 0 to 0, but it's got a high or low, depending on the sign, centered on the fault. So the strain is maximum right where the fault location is. And the magnitude of the strain depends on two things. One, it depends on the spatial scale that we're measuring here. But that signal, the width of that signal, actually tells us something about the size of the fault. It tells us something about how much of the fault is logged. And then it also tells us the point where the very peak strain is, that tells us about how much of the fault is locked, or perhaps I could say how coupled the fault is. So those two pieces of information, the size and then how much of the fault is locked, is encapsulated in the peak of that strain as well as the width of that profile. Now let's look back at the San Andreas, and again here's the velocities. Here we see velocity going from low on the Nevada side of the California line to high as you cross the fault. So we're going from low to high as we go from east to west, or northeast to southwest as you cross the fault. So this is essentially what I've drawn here. You have very low velocities on the North American side of the plate, and this is the North American plate on the east side of the San Andreas. And you transition to very high velocities as you cross the San Andreas from the North American to the Pacific plate. Now let's look at a profile of these plots, and I think somewhere here I have a profile. Oh, here it is. Right. Let me zoom out just a touch. So I've got three profiles here. We're just going to look at this bottom profile, which is on the part of the San Andreas fault that's locked. Actually, there's some parts of the fault that are creeping. We're not going to talk about that today. But here's a profile of GPS velocities from the from the Pacific side, that's this left-hand side of the plot, over to the North American side on the right. So you can see exactly what I've drawn here. The numbers are a little bit different, but you can see them there. So you go from low velocities on the North American side to high velocities, and you have this very gradual transition from low to high, centered essentially on the San Andreas fault. And I've got the fault location marked there for you. So if we were to take a smooth line, now these are point measurements, right? These are GPS measurements. They're a little bit noisy, and they've also been projected. So the GPS stations vary in 2 dimensions, not just 1 dimension across the fault. So there's some noise here. You can see the black dots are from different GPS stations, and we also have some missing data, so we don't have data everywhere. But you could draw a smooth line through this scatter plot and essentially come up with something very similar to what I have drawn on the blackboard. And then we can take a derivative of that smooth line, and we would get a line which looks something very much like this, the red line I've drawn, where the peak of the, and you can actually even see just by looking at these dots, that the peak slope, the peak, the highest magnitude of the slope is happening right here, right centered on the San Andreas fault. And then you transition to a smoother slope going towards 0 as you get towards either side. And we don't have enough data because we run into the ocean actually to see the full kind of flattening out here on the Pacific side. But you do see it on the North American side. And if I were to show a few more data points over here to the east, then they would show that the velocities essentially go to 0. So we see exactly what we see on the board. So what does this tell us? Basically, we can just simply look at the GPS data, and we already know where the fault is because we know where the strain rate is highest. So we don't need to know where the San Andreas fault is. I could give you this profile, and you would be able to tell me based on the strain rate, based on the derivative of the velocities. Now you would have to smooth the velocities, you'd have to take the derivative, but you would be able to tell me where the San Andreas fault is, or where a fault is based on the data. Maybe you wouldn't know it's the San Andreas. Maybe I would just say, here's some data, tell me where the faults are. And you would be able to find the faults based on the strain rate. Not only that, you'd be able to tell me something about the earthquake potential on those faults based on the magnitude of the strain, the magnitude of the peak strain, how negative or positive this peak in the strain rate is. And you'd be able to tell me something about the size of the faults from the width of the strain rate distribution around the fault. All of that information is encoded or encapsulated in the GPS data. And the same holds true actually for INSAR. We'll talk about that in another video. So using this geodetic data, information on surface velocities tells us about the size and amount of the fault that's locked and is accumulating strain and is going to rupture in a future earthquake. So this is the importance and value of geodetic data for earthquake hazard.